Right. So in the previous class, we discussed about simple stresses. That means if there is different types of simple loads. So we discussed how to compute the stress value, and also we discussed about the design equations. How we can, based on the design equation, how we can determine the size of the component. So that we'll see while solving some of the problems. We'll discuss those things. So next comes off next kind of load, which is we will call it as a eccentric loading. So what is the eccentric loading? So far, whatever you take in that, the load is suppose if first case if we take a tensile load. So in case of a tensile load, the load line or line of action of the force will pass through the centroid of the cross section. So in that case, we won't call it as an eccentric load. An eccentric load is nothing but whose line of action is not passing through the centroid of the cross section. Then we'll call it as eccentric load, even though it is applied along the axial axis, along the axis. That's why it is called axial load. Axial load means a load which is applied along the axis or in the direction of the longitudinal axis. We'll call it as axial load. But if that axial load, line of action of that axial load coincides with the centroid of the cross sections, then we'll call it as a simply axial load. But if there is any offset distance or any eccentricity is there, we'll call it as eccentric load. So then how we'll calculate the stresses when there is an eccentric loading? So that we'll see now. So there are certain mechanical components subjected to an external force. Force may be either tensile or compressive, but which does not pass through the centroid of the cross section. So if the load line does not pass through the centroid of the cross section, then we'll call it as a eccentric load. So that is the important point you need to remember. So now how we can find the stresses when there is an eccentric load? So okay, so here this is one of the typical example where you can say there is an eccentric load. Suppose I have a bar having some rectangular cross section. So here this is the one view and this is the cross section view. So here the cross section is rectangle. So this is the centroid for the cross section. Now this is our longitudinal axis. The longitudinal axis is nothing but the axis along the length. So this is the length direction, or this is the length of the bar. So along the length the load is applied. See here this P is applied along the length. So if this P is applied here, so that means if this passes through the centroid, then we simply will call it as axial load. So but now if we take this particular case, the loading here, so the load is applied at this point, not at this point. So that means, so you can see here the point of application of load is at this location, not at the centroid. So therefore, whatever this distance will offset distance is there, we'll call that one as eccentricity of the loading, E. So that offset distance, so here also you can see, here also you have shown it as E. So if this kind of load is there, we'll call this one as an eccentric loading. So now to find out the stresses when a component is subjected to eccentric loading, so how we can find the stress values? So first what we'll do is, so we don't have a direct formula for computing stress when the load is an eccentric loading. So what we have to do is, we have to convert that one into load which is acting at the centroid. So here the load is not acting at the centroid, then what we'll do is we'll convert this one to the load acting at the centroid. So to do that, we need to use the principles of mechanics again. So here eccentricity load is there. If I transfer this load from one plane to the another plane, whenever, so I think you might have studied this in our engineering mechanics itself. So if you want to transfer the force from one plane to the another plane, the net effect will be the same load in the same direction plus a movement. So given by the force multiplied by the offset distance. So that is the principle here. So that's what according to principle of statics, the eccentric force P can be replaced by a parallel force P. So now this is the force. Here we are replacing this force by a parallel force. So parallel means they are in the same direction. But only thing is here it is acting eccentric, but here it is passing through the centroid. So a parallel force passing through the centroidal axis So this is one thing. Then with a couple, that means plus. So not only that. So whenever the eccentricity, so it is not only a axial load plus a bending moment or a couple. You can say couple is nothing but a moment. So and the magnitude of the couple is given by the magnitude of the load multiplied by this eccentric distance between the centroid to the line of action of the force. So that will take it as the couple, because here it is P into E. So the couple. So therefore, you need to replace this eccentric load, single eccentric load by two loads. Here one is direct tensile load, that is load which is passing through the centroid, and the magnitude of that load is same as the magnitude of the eccentric load. And in addition to that, you have a moment or couple. So here the magnitude of the couple is P into E, where P is the magnitude of the applied force and E is the eccentricity. And the direction of this couple is decided based on this. See now, if I take, this is our axial line, so then what is the couple of, or what is the moment of this force about this longitudinal axis? So now here, the moment of this force about this longitudinal axis, here it is in anti-clockwise direction, because this force will try to rotate this block in the anti-clockwise direction. So if I look at from this point, so here I need to take that couple is also in anti-clockwise direction. So for equilibrium, what you have to do is you have to apply on both sides. So then only you can apply sigma f is equal to 0, then it is equal to 0, it will be in equilibrium. In similar manner, here you need to take a clockwise movement or movement due to this force. So here it is in this direction, clockwise direction, you need to take clockwise direction here. So that means, so now the net effect, what you can say here is, the net effect is whenever there is an eccentric load, so if you want to simplify that load in order to compute the stresses, you need to consider an axial load, and then you need to consider a movement. Sometimes the movement may be bending movement, sometimes the movement may be twisting movement. So depending upon that, you can identify the stress. If it is a bending movement, we'll calculate the normal stress. If it is a twisting movement, we'll calculate what is the torsional shear stress. So now, once you calculate it individually, so for this we know how to compute the stress. So simply this is axial tensile load. So in case of axial tensile load, the load is, the stress is uniform at any cross section. If you take a cross section here, so it is going to be uniform. So that is shown it here. This is the, in case of axial tensile load, you have a uniform stress, and that magnitude of that uniform stress is given by P divided by the area of this cross section. So that's what shown it here, P by A. So the magnitude or the intensity of the stress is P by A. So that we know. Similarly here, if you take this, it is subjected to a bending moment here. So if how we can decide whether the moment is a bending moment or twisting moment? If the moment is applied or acting about the longitudinal axis, I can say it is a twisting moment. So if it is acting about this axis, something like this, then I can say it is twisting moment. But here it is not acting about this axis. So here, this is the axis it is acting. So about this axis, it is acting, this couple is acting something like this. That means this is the axis which is perpendicular to this. So now that means if any movement which is acting perpendicular to the longitudinal axis, we call it as a bending moment. Maybe of course, if it is, it may be something like this, or it may be it may act about this axis also. There may be two cases. Either so perpendicular direction for this longitudinal axis means you have the direction something like this, that is also perpendicular. You can have something like this. This is also perpendicular. So these are the two things. So now, if the moment is acting about this axis, either about this axis or either about this axis, we'll call it as movement. If the moment is acting about this axis itself, this longitudinal axis, we'll call it as a twisting moment. So now if you consider the case here the moment is acting about this axis. So like this, if I draw like axis like this, then only I can say this is the direction. So therefore, it is not the longitudinal axis, we will need to take it as a bending moment. So we already seen how to compute the stress due to bending moment. So here, because of this bending moment here, so this top layer, so the bending moment is something like this. If I apply to that cross section, the bending moment is something like this. So this, sorry, it is something in this direction. It is like this and like this. So because of this kind of bending moment, so this top layer is subjected to tension and bottom layer is subjected to compression. So therefore, you have a tensile stress here and you have a compressor stress. At the neutral layer or at the centroid, you have a zero stress. So therefore, I can plot the stress something like this. So that means here you have two kinds of stresses. One is a uniform stress because of direct load and a bending moment. So it is varying from tension to compression. So compression is there at the bottom layer and tension is there at the top layer. At the centroid it is zero. So it is changing from tension to compression. So now to find out the resultant stress because of this loading, so you need to use the principle of superposition. That means you need to sum up these two. You need to superimpose one upon the other. So you have a two stress states here. This is 1 and this is 2. Now I need to club or superimpose one upon this 2. Then if I do that, I'll get something like this. So here this side it is negative. So here it is positive. If I take the algebraic sum negative plus this positive, here this negative value is larger. So therefore I'll get only a small amount here. So if you come to this end, both are positive. This is positive and this is positive. So it is going to be higher in magnitude and compared to this one and this one. So that means simply you need to take the algebraic sum at any point. So similarly, if I take this point here at the neutral axis, so only you will get this is the stress value. This stress value is 0. So that means exactly the height here, whatever you got at the neutral axis, this is same as this. So because here you don't have any stress because of bending. So like this, you can calculate the stresses when there is an eccentric loading. So first you need to identify, you need to convert that eccentric loading, especially axial loading, eccentric axial loading into a direct load plus a bending moment or maybe a twisting moment. You need to identify the direct about which axis the couple is acting. So based on that, you can classify whether it is a twisting moment or bending moment. So then you need to compute the stresses. Suppose if it is a twisting moment here, you cannot use the principle of superposition because the direct load, because of this, you will get a normal stress. So generally we'll use sigma symbol for that. So suppose if here it is the bending, if you have a twisting moment, because of that you have a shear stress. Always when a component is subjected to a twisting moment, a torsal shear stress will induced. Simply you cannot add because this nature of stress is a normal stress, but this is a shear stress. Simply you cannot use principle of superposition in this case. If both the stresses are normal stresses, then only you can use the principle of superposition to compute the resultant stress. So here, because of direct load you have a normal stress, because of bending also you have a normal stress, directly you can use that principle of superposition. Means you can simply sum up those values. You can take the algebraic sum of the stresses so that you can find the resultant stress. But if you have one normal stress and one is a shear stress, you cannot use the principle of superposition here. So this kind of stress system, we can call it as a complex stress system. We'll discuss this one later. As of now, even though there is an eccentric load, because of eccentric load, only normal loads are produced. So in case of this axial loading, so this principle is valid when the load is axial loading only. So therefore, you can use the principle of superposition to find out the resultant stress. Okay, so that's what I have written here. So figure B. So this is figure A, the axial loading case. The figure B, the force causes a uniformly distributed tensile stress of magnitude P by A. So we know this for this figure. From this figure, you can clearly understand that it is subjected to a tensile load. So direct tensile load. So that's why I'm using here especially direct. So that is the difference between eccentric and direct. Direct, whenever you say direct, means the load line is passing through the longitudinal axis. So then we'll call it as a direct loading. Otherwise, it is a eccentric loading. So because of direct load, direct tensile load, we know the magnitude. There is a direct stress which is uniform throughout the cross section, and its magnitude is given by P by A, where P is the applied load and A is the normal cross sectional area. Then this figure C shows that the bending moment because of couple causing bending stress of magnitude. We know the formula for bending stress also. Bending moment divided by I into Y. So Y is nothing but the distance of the layer from the neutral axis. If neutral axis lies here, you need to measure the distance. Of course, you need to consider in the cross section here. This is your neutral axis, NA. Then if your y is measured from this point, so wherever you want to find the stress, you can calculate the stress by substituting what is y value. Then we'll use the resultant stress. So to compute the resultant stress at the cross section, just using principle of superposition. So therefore, principle of superposition name itself suggests that it is a superimposing one upon the other. So then only we'll call it as superposition or superimposition. So that means superposition is nothing but the superimposition. So you need to place one upon the other, then you need to find the resultant. So this is how you can calculate the resultant stresses when there is an eccentric axial load. So now what we'll do is, so we'll consider some small simple problems. You might have solved all these problems in the earlier courses also. Anyway, we'll review them again and we'll try to design the component. Design of the component in the sense, we'll try to find out what are the dimensions of the component based on the given conditions. So now we'll see some one by one. We'll see problems related to the all kinds of loads so far, whatever we discussed. We'll take up one problem corresponding to each one, then we'll discuss it. So now this is the first example problem here. So here the problem is a cast iron link is required to transmit a steady tensile load of 45 kilonewtons. Find the tensile stress induced in the link material at section AA and section BB. So here it is not a design problem, it is an analysis problem. So generally we have two kinds of problems. So one is design problem, another one is called analysis problem. So in design problem, what we need to do is, they will give you the stress values, or we need to compute, they will give you in analysis problem, like I said, it is an analysis problem. In analysis problem, all the dimensions are given to us and asked us can calculate what are the stresses. That's what asked in this problem. Find the tensile stresses. So that means you need to find the magnitude of the tensile stress. So this kind of problem. So here the dimensions are already given. See, cross section at this location he has given one cross section. At section AA, this is the cross section, a rectangular cross section, and he has given the dimensions for the rectangular cross section. It is 20, 45, and all dimensions are in mm. He specified that also. So it is a rectangular cross section at this location. So he has given the dimensions, so I can calculate easily what is the cross section area. If I know what is the load acting at this section, I can easily calculate the stress. Direct tensile stress is nothing but E by A. So this kind of problem we'll call it as an analysis problem. So analysis in the sense, dimensions, so everything is given to us. So he asked us calculate what are the stress values. Other kind of problem is, they may not give these dimensions. Let us say out of this 45 and 20, they'll give only one dimension 45 and they won't give this 20 value. But they will give you the allowable strength of this material. So that means only this much of tensile load is allowed in this material. So like that they'll give. So then based on the design equation, we can compute what is the dimension required here. So whether 20 is sufficient, or if 20 is not sufficient, then I'll go for 30 or 40 or something like that. So that kind of problem. So that means if I am deciding the dimensions of the component, then I'll call it as a design problem. If already dimensions are given and they may ask whether that material is safe or not, that may be one kind of question, or other kind of question is just they will ask you find out what are the values of stress values. Then that is the other kind of problem. So these kind of problems we call it as an analysis problems. So here this problem comes under the analysis problem category. So now here he has given the dimensions at both the sections. See here at the section 1, section AA. So this is the first section, section AA. Here the cross section he has given it as a rectangle. So the rectangle dimensions is 20 and 45 mm. So simply you can easily calculate the area of the rectangle is nothing but breadth into height, 20 into 45, which comes out as 900 mm square. So then if I want to calculate the stress at this location, then what I need to do is, I'll cut it here and I draw the free body diagram for this. So here this link is subjected to a tensile force here shown something like this P, and the magnitude of the P has given it as a 45 kilonewtons. So now if I cut it here, if I draw the free body diagram for this, if I consider it, it will be something like this. So this side it is subjected to a force of P. So then if I cut it here for equilibrium, so if you apply sigma F is equal to 0 or sigma Fx, if I say this is the x direction, horizontal direction, I'll take sigma Fx is equal to 0. then what I'll do is, so I'll take here the force as some R, I don't know, unknown force, I'll take it as R. So then if I apply this equation, what I'll get it here? So generally I'll take rightward forces as positive and leftward forces as negative. Then if I apply the force equilibrium for this free body diagram, so R is positive and P is negative. R minus P equal to 0. This is the equation what I am going to get. So from this I can write our R is nothing but it is equal to P only. So that means this cross section is subjected to a tensile force of magnitude P. So I know P value, load on the section, I know the cross sectional area. Then obviously the stress is going to be sigma is equal to P by A. Our formula is, why I am using sigma here? Because it is a load which is acting normal to the cross section. So that normal to cross section means perpendicular to the cross section. So I have to use this sigma. Here it is going to be normal stress only. So therefore P is 45 kilonewtons. So I want to convert that one into newtons. So 1 kilonewton is equal to 10 power 3 newtons. So therefore 45 into 10 cube I need to take, divided by area of this cross section, which is 900. So then here the units for the load I have taken it as newtons. Even though it is given in kilonewtons, I converted that one into kilonewtons, that kilonewtons into newtons just by multiplying the 10 power 3. Now it becomes Newton. Then the area for units for this area is 20 mm into 45 mm, which is 900. It becomes mm square. So the units for the area is mm square. Therefore the units for our sigma now it becomes Newton per mm square. So if I simplify this, what I'll get is, so here 2 zeros if I can cancel out here, and also 9 5s. So what I'll get it is 50. The stress in the cross section at this location, at the section AA, is nothing but 50 Newton per mm square. So in most of the books, sometimes they'll write it as Newton per mm square, and sometimes they may write it as 50 MPa also. 50 MPa. So this is the other unit for stress. We will follow most of the cases. So MPa means it is megapascals. So 1 Newton per mm square is equal to 1 MPa. Like I written here, 1 Newton per mm square. I am taking it as 1 MPa. How it is equal? How these two are equal? Let us see. So we know Pascal. One Pascal is nothing but, we'll define as Pascal as Newton per meter square. Pascal is Newton per meter square. Megapascal means 10 power 6. Mega means it is 10 power 6. Giga means 10 power 9. Kilo means 10 power 3. That's what we are taking here. Kilonewton is there. Whenever kilo is there, you need to take the multiplication factor as 10 power 3. Whenever mega is there, you need to take the multiplication factor as 10 power 6. Whenever there is a giga term is there, that is 10 power 9. So now what I am saying here is 1 Newton per meter square mm square is equal to 1 MPa. 1 MPa is nothing but 1 into 10 power 6 Newton per meter square. So is these two are equal or not? I need to check that. So here numerator unit is Newton, that's okay, fine. But in denominator here you have mm square, here you have a meter square. So now what I'll do is, I want to convert this mm into meter, meter into mm. So how many mm are there for a meter? 1 meter is equal to 1000 mm, isn't it? So that means I'll write that 1000 as 10 cube. So 1 meter equal to 10 cube mm. So now, but here what I have, meter square is there. If I take square it this side, what I need to do is, I need to square this side also. So if I square this, what I get? 10 cube square is nothing but 10 power 6. 10 power 6, mm will become mm square. So therefore, 1 meter square, I will write it as 10 power 6 mm square. So that means if I substitute that one here, I have 10 power 6. Then Newton is there in the numerator. In the denominator, I have 10 power 6 mm square. That means this 10 power 6, this 10 power 6 will cancel out. Finally, what I left with? I left with only 1 Newton per mm square only. So that means you can, wherever you come across either 1 Newton per mm square, you can take that one as 1 MPa. So they are equal. Or if you come across 1 MPa means you can understand that one as 1 Newton per mm square also. Either way. So we'll use these two interchangeably in all our problems. While solving the problems, sometimes we'll say MPa, sometimes we'll say Newton per mm square. Not only that, in some instances they'll give in Newton per meter square also. Then we need to convert that accordingly. See here, so I cannot say here if I take these dimensions, even though he has given an mm, if I convert this one into meters and if I substitute those things here, then it becomes Newton per meter square, not Newton per mm square. That means whatever units you are following, so you need to follow the consistently and accordingly you need to write the unit for also the stress value. That is also very important. See here, I solved the problem, so I got the answer. The magnitude I got it 50, but instead of 50 Newton per mm square, if I write 50 Newton per meter square, then it is going to be wrong. So even though your magnitude you are calculated properly, if you not specify the unit properly, it is going to be wrong. Because if you design for 50 Newton per meter square instead of 50 Newton per mm square, then if you apply the actual load that 45 kilonewtons, your component is going to fail. So you may think of that only I written the unit is wrongly, but our value is correct. Even though unit is wrong, your component is going to withstand. So that means the design engineer failed there. So that's why your answer is also wrong. So don't think that just by writing the 50, my entire problem is correct. If you write the units wrongly, then also your problem is entirely wrongly. You are going to get only 0 marks. Even though you calculated you write the formula properly and you done everything properly, while at the end, if you write the units wrongly, instead of Newton per mm square, if you write Newton per meter square, gone. You are going to get only 0 marks. So because there is a lot of difference. The stress of 50 Newton per meter square is different when compared to 50 Newton per mm square. So 50 Newton square, if you write that one as in Newton per mm square, it is going to be 50 into 10 power minus 6 into Newton per meter square. So see the difference. You have to take a 50 Newton per meter square stress, but you are calculating and you are written it as 50 into 10 power minus 6. That means, so there is no stress at all. 10 power minus 6. If you compare that, it is going to be a very negligible value. So that means you are saying that there is no stress at all in this component, so which is very wrong. So that's why always be careful while solving the problem. Not only solving the problem, you need to write you need to specify the proper units also. Then only it is called a proper design. Which simply if you say some number, it is not going to be design. And similarly, if you take another way, if you have another problem, just I need to calculate the dimension. So now I arrived the value as 20. Then I need to specify its also whether they are 20 mm or 20 meters. If you specify them wrongly, again your design is wrong. Instead of meter, suppose if the dimension is in mm, if you say it is 20 meters, then it is wrong. So you have to design a 20 mm rod, but you are specifying it as a 20 meters rod means see how much difference is there in the design. So therefore, even though you are making a small mistake in specifying the dimension, it is going to lead your entire design or entire problem is going to be wrong. So be careful about that also. Okay, don't think that okay, only magnitude is important, units are not important. So magnitude is important as well as units also very important. So you remember that point while solving the problems. Okay, anyway, so we already seen how to compute the stress at this section. Then we need to consider section B. So at this section, he has given the section B cross section details. He has given here. Is that so? For A, he has already shown in the diagram itself, in the rod itself. So for section B, instead of showing it here, he has taken an upside section and he has shown the dimensions here. So here the section at this location again it is a rectangle, but it has some hole is drilled at the center. So therefore here this dimension is 40 he has given and the stop dimension is 75. So now we need to compute the area for this. So this area it is, we already know the area of this section is nothing but 20 into. You can calculate in either way. So only thing is I can consider what is this area plus what is this area. That is one way of doing it. Or else you can calculate this total area. So from that you can subtract this area. So like that also you can do it. So first what I'll do is I'll calculate the total area. Total area is 20 into 75. Then I need to subtract this. So that this area is 20 into 40. So 20 already I taken common. So since I have to subtract, I have to take 20 into 40. I'll write something like this. So 20 into 75 minus 40. So you'll get the area. So here also it is axially applied load. See, you can see that it is passing through the longitudinal axis. So you have only direct stress. The formula for direct stress here also it is again P by A. So but only thing is when compared to this section, here the area is different. That is the only thing. So you'll get a different magnitude. So here 75 minus 40 you'll get 35. 35 into 20 you'll get the area as 700 mm square. 700 mm square. So load remains same. Here also P, and on this section also it is P. Only thing is the magnitude of stress is going to change. So I'll take this is sigma B. So that means the stress at the section BB. So which is again the load is 40 into 10 cube. 45, sorry, not 40. It is 45 kilonewtons is given here. So 45 into 10 cube divided by 700. So again the units are load we are considering in newtons. Area we are taking it as mm. So mm square. The units for this stress is also Newton per mm square, or instead of writing Newton per mm square, I can write it as MPa also, because 1 Newton per mm square is nothing but 1 MPa only. Okay, so I'll show the numerical values here. See, you can see the solution here. The cross-sectional area of the link at the section AA is A1. He has taken it as A1, which is 45 into 20. So here, this is the cross-section, which is 900 mm square. Then the tensile stress at this point is nothing but P by the area at this location. He denoted that area as A1, so therefore P by A1, which is 45 into 10 cube divided by 90, which is given as 50 Newton per mm square. I can write that one as 50 MPa also. Just now I said 1 Newton per mm square is nothing but 1 MPa. So then we'll consider the section at this location BB. So then the area is nothing but, just we already calculated, the area is, he denoted that area as A2, which is nothing but 700 mm square. 20 into 75 minus 40, it is 700 mm square. Then the tensile stress at this section at B is nothing but P by A2. So 45 into 10 cube is the load P, and A2 is 700. So if you substitute that, you will get 64.3. So which is nothing but 64.3 MPa. So like this, you can calculate the stresses in the given section. So then we'll consider one more problem like this. So this is the second problem. So what he asked is, so here this is a design problem. Previous one is an analysis problem. Here this is a design problem. So why I am calling it as a design problem? So he asked us find the diameter of the bar and the pin. So that means if he specified to find the dimensions of a component, we'll call it as a design problem. So now we'll describe this problem, what he has given, and then we'll see how we can find the dimensions of the bar, or that is the diameter of the bar and diameter of the pin. So here what he has given is a pull. Pull means, again it is a tensile force. So the tensile force can be designed as, or can be termed as pull. Push means it is a compressive force. So here it has given a pull. See, you can see here, I have shown it as a tensile force only. See, what happened to this cursor? Okay, right. So he has shown it as a tensile force. So tensile force in the sense, always the load will move or direct away from the body. This is our body. So the load is directing away from the body. So compressive means the load should direct towards the body. So it should, the direction should be something like this. We'll call it as a compressive. Or pushing load. We'll call it as pushing load. Whereas the given load is a pulling load here. It is moving away from the body. So a pull of 80 kilonewtons is transmitted from bar X to bar Y. So he has given bar X and bar Y also. This is the bar X he has taken. So which is sectioned here, and that what you can say blue color sectioning is there, that is corresponding to this bar X. Then bar Y is sectioned here, so the section is highlighted in what you can say pink or red color. So this section is corresponding to bar Y. So we already studied these things in our CMDP. So how we can section different materials are like that. We already discussed those things in the CMDP course. If you recall that, from that you can easily understand this. So which portion is corresponding to which bar. So this top one, this portion and this portion, we will call them as the ports. These ports are corresponding to your bar X, and this is the rod, your bar Y. So this entire thing is going to be your bar Y. So that's what he has given. A pull of 80 kilonewtons transmitted. So load is transmitted from bar X to bar Y. So it is 80 kilonewtons here, that is transmitted to here for this bar Y. If the maximum permissible tensile stress in the bar is 100 Newton per mm square and the permissible shear stress in a pin is 80 Newton per mm square, then find the diameter of bar and the pin. So diameter of bars, both the bars here asked, both the bars as well as the diameter of the pin. So how we can do this? So to find this one, we need design equation. To use the design equation, so you have a set of design equations. So first you need to identify what is the nature of the load acting on the, we'll take one by one. First we'll take the design of bar X, then we'll take the design of bar Y. So then I think the diameters of the bar X and bar Y here it is same only. So if you design for bar X, it is same as for bar Y also, whatever diameter you are taking. Here if I take this one as D, even this is also D, diameter D, so no need to design Y separately, provided if you already design the X. So and similarly, if you design Y, no need to design X also, because they are having same diameters. So now we need to identify what kind of load is acting on this bar. So let us say I choose Y instead of X, I can choose Y, or I'll choose X instead of Y. That is our choice. You can choose X or Y, it doesn't matter here, because both are same only. Both are subjected to same load and same kind of load. So now if I take this bar, if by looking at this bar Y, so this 80 kilonewtons, how it is acting? So now I will ask your response also. Simply explaining it, I don't know whether you are following it or not, or whether it is clear for you or not. So we'll have some interaction there so that we can easily, other people also understand it easily. So this is bar Y. So now, can somebody respond how this load is acting?
Tensile, sir.
Okay. So before going to the tensile, we can say that it is acting along the longitudinal axis, right? This is the axis, right?
Yes, sir.
So therefore, it is acting along the axis. So we'll call it as an axial load.
Axial load.
So axial load, then we'll decide if it is towards the body, it is compressive. If it is away from the body, we say tensile. So whatever is said, it is correct. But only thing is, it is an axial load. So and also tensile load. Okay. Anyway, I think time అయిపోయింది 11:15 is already. 11:30 దాకా కదా మన క్లాస్.
11:30 దాకా సార్.
Yes, sir. 11:30.
Okay. So then we'll continue. So therefore, for this rod, it is a tensile load. Right. Very good. So I agree. So once you know the tensile, it is tensile load, we can easily calculate the stress due to this tensile load. What is the formula for our stress?
Sigma equal to load by area.
Load by area. So therefore, here what we need to do is we need to calculate the area of this section.
Area of this section.
You can take any section here. You can calculate the area. But here he has not given the diameter. So what type of section he is saying that diameter means? He is saying diameter means here you have a circular cross section. See, you can see the symbol also here. This symbol also indicates it is a circular cross section. This is the shaft cut, you can say. So this kind of cut, if you observe that, you can say it is going to be a generally, or else. So if you don't bother about this one also, here he clearly specify that he asked us find the diameter of the bar as well as the pin. So that means diameter means it is a circular cross section only. So therefore, I don't know the diameter, but I'll assume the diameter as D. So in case of circular cross section, I know the area. So what is the cross-sectional area formula? 5 by 4 d square, where d is the diameter. Sorry? Huh? Endama? Yeah, somebody, I didn't get you what you are saying. Okay, so right. So I know the area, I know the load, then I can easily calculate the stress. Stress is nothing but P by A. So, but in that P by A, area is in the form of unknown diameter D. So now I'll take, this is the induced stress. I'll take this induced stress value and I'll equate it to the allowable stress. So that is what my design equation. What our design equation here is, we need to compute the induced stress and we need to equate that induced stress to the allowable stress. So allowable stress value is given for us here. So he has given the permissible tensile stress, permissible or allowable, both are same only. So don't think that permissible stress is different from the allowable stress. Allowable stress is also same. So I also told that sometimes you may call it as permissible design stress also you will call, or working stress also you may call. So whatever it may be, permissible or allowable or design or working, all these are same thing only. So therefore, he has given that value, 100 Newton per mm square is given. So now we have design equation. So design equation is P by A is the stress induced in the bar. It should be equal to your sigma allowable, or I can write it as sigma within the brackets also. So now from this you can easily calculate the unknown area. So P is given, sigma is given. So then only thing is, first I'll compute what is the area. So I'll get some numerical value from this equation for area, but this area, our area is nothing but 5 by 4 d square again. So in this, only unknown for me is only d now. So I can solve this equation so that I can calculate the diameter of this rod. Then coming to the pin. So this is how I can solve for the diameter of the rod. Once I know this diameter, I am taking the same diameter for this also, because they are appearing same. So it doesn't mention whether they are different or not also. So even if we assume they are different, okay, let us say this is different from this. So okay, right, I'll take a section here. Again, he said this is also circular cross section. Let us assume the diameter has some d1 here. Here we have taken d, I'll take here d1. So now again, what is the formula for the stress here? Here also it is axial load only. The magnitude of load is same, 80 kilonewtons only. Then your induced stress is P by A only this, and the allowable stress is also same, that is 100 here. So if you solve that equation, you will get, even though you are considered it as a different value, you will get the same value here. Whatever value you got it here, you will get the same value here also, because the formulas are same, the load is same, the allowable stress is also same. So therefore, the area also should be same. Then in that case, whatever diameter you have here, you will get the same value here also. In that way also, I can verify that. Okay, so that is about how we can calculate the diameters of these two rods. Then coming to the pin. So now your axis of the pin is something like this. This is the longitudinal axis, but here the load is acting something like this. So is it an axial load? This force is, this load is acting as an axial load to this pin?
Load, sir.
So for that, what I'll do is, I'll transfer this one to the free body diagram for this. So now, if I do that, if I transfer it at this location, so then what happens? Here, I'll transfer here the load something like this. So, like this. So then, this is P. This is P. So now what kind of load it is? For this cross section, it is like a tangential or a normal?
Normal.
Normal and 11. Suppose I have a bar something like this. So this cross section is so 3-dimensional, if you take the 3-dimensional. Okay, this is the cross section. Antena cut chesti idi cross section vachedi.
Axis perpendicular ga unte normal ga sir.
Along the axis unte normal ra, axis perpendicular kadra babu. Din axis ante idi axis endi idi kada? Axis ki normal ante enti? Asalu normal ante enti? ఒక పాయింట్ కి నార్మల్ ట్యాంజెంట్ అంటావు కదా నువ్వు. నార్మల్ అంటే ఏంటి? సపోజ్ ఒక సర్కిల్ ఉందిరా నాకు, ఈ సర్కిల్ ఓకే, లేదా ఈ క్రాస్ సెక్షన్ ఉంది చూడు, ఈ క్రాస్ సెక్షన్ కి నార్మల్ డైరెక్షన్ అంటే ఏంటి? ఈ క్రాస్ సెక్షన్ కి పర్పెండిక్యులర్ డైరెక్షన్ ని నార్మల్ డైరెక్షన్ అంటామా, రైట్? ఇందాక రెస్పాండ్ అయినా మా నీ డౌట్ ఒకసారి క్లియర్ అవుతుంది చూడు. ఇప్పుడు సపోజ్ నేను ఇప్పుడు ఈ లోడ్ చూసుకున్నా కదా, ఈ లోడ్ వల్ల ఇప్పుడు లెంత్ ఏమవుతుంది? ఇంక్రీజ్ అవుతుందా డిక్రీజ్ అవుతుందా? అప్పుడు లెంత్ లో చేంజ్ ఉంటుందా ఉండదా?
ఉంటుంది సార్,
అమ్మా
ఉంటుంది సార్.
సో మనం ఫస్ట్ డిస్కస్ చేసాం కదా, లెంత్ చేంజ్ అయిందంటే అది నార్మల్ లోడ్ అని, నార్మల్ స్ట్రెస్ అని, దాని నుంచి వచ్చే స్ట్రెస్ నార్మల్ స్ట్రెస్ అని. అట్లా కాకుండా క్రాస్ సెక్షన్ షేప్ చేంజ్ అయింది అనుకోండి, టూ థింగ్స్, లోడ్ వల్ల అప్లై చేసే లోడ్ వల్ల టూ థింగ్స్ విల్ గోయింగ్ టు హ్యాపెన్. ఒకటి ఏంటంటే దాని కాంపోనెంట్ యొక్క లెంత్ ఇంక్రీజ్ అవ్వచ్చు, డిక్రీజ్ అవ్వచ్చు, అది ఒకటి కేసు. అట్లా కాకుండా లెంత్ ఇంక్రీజ్ అవ్వలేదు, డిక్రీజ్ అవ్వలేదు, నీకు క్రాస్ సెక్షన్ షేప్ మారింది. సపోజ్ ఇనిషియల్గా నా క్రాస్ సెక్షన్ రెక్టాంగిల్ ఉంది, ఇక్కడ రెక్టాంగిల్ కాస్త నేను అప్లై చేసిన లోడ్ వల్ల రాంబోస్ లాగా ఏదో మారిపోయింది అనుకో, దాన్ని ఏంటంటాం? దాని వాట్ కైండ్ ఆఫ్ లోడ్ విల్ కాల్ ఇట్ యాజ్? ఇదే బార్ ఇప్పుడు నేను ఇక్కడ లోడ్ అప్లై చేస్తే ఏమవుతుందంటే ఈ బార్ ఎలాంగేట్ అవుతుంది, అంతేనా? ఇది లెంత్ అనుకుంటే నువ్వు, ఈ లెంత్ పెరుగుతుంది, అంతేనా? సో దెన్ దిస్ కైండ్ ఆఫ్ లోడ్ విల్ కాల్ ఇట్ యాజ్ నార్మల్ లోడ్. సో నార్మల్ లోడ్ అని ఎందుకు అంటున్నాం అంటే, ఇక్కడ ఈ క్రాస్ సెక్షన్ తీసుకుంటే నేను ఈ క్రాస్ సెక్షన్ కి ఇది పర్పెండిక్యులర్ డైరెక్షన్ లో ఉంది. సో నార్మల్ మీన్స్ 90 డిగ్రీస్, నార్మల్ మీన్స్ 90 డిగ్రీస్ టు ద క్రాస్ సెక్షన్. సో ఈ క్రాస్ సెక్షన్ కి ఇది పర్పెండిక్యులర్ ఉంది కాబట్టి ఇది నార్మల్ లోడ్. అట్లా కాకుండా సపోజ్ నేను ఇప్పుడు ఇట్లా అప్లై చేసే లోడ్ అటు పైన ఇటు కింద, సో ఇది పిఏ, ఇది పిఏ. సో ఇది 3 డైమెన్షన్, నేను 2 డైమెన్షన్లో చూపిస్తానంటే ఇది క్రాస్ సెక్షన్. నాకు ఈ క్రాస్ సెక్షన్కి నేను ఇలా అప్లై చేశాను. సో క్రాస్ సెక్షన్కి ఇప్పుడు ఇది పర్పెండిక్యులర్ ఉందా? రెస్పాండ్ అవ్వాలి ఎవరో ఒకళ్ళు.
No sir.
No sir.
This is a tangential load, right?
Yes sir.
So because of tangential load, you have a shear stress. So the same thing here. ఇక్కడ నీ క్రాస్ సెక్షన్ ఇక్కడ ఇలా ఉంది, క్రాస్ సెక్షన్ ఉంది, క్రాస్ సెక్షన్ కి పర్పెండిక్యులర్ ఉంది ఈ లోడ్. అలానే ఈ లోడ్ ఇక్కడ క్రాస్ సెక్షన్ అని ఇక్కడ కట్ చేసాం అనుకో, ఇక్కడ క్రాస్ సెక్షన్ ఇక్కడ పర్పెండిక్యులర్ ఉందా, టాంజెన్షియల్ ఉందా? ఇక్కడ కట్ చేశాను నేను, ఇందాక క్రాస్ సెక్షన్, ఇందాక బార్ కేసు తీసుకో, ఇక్కడ కట్ చేశాను నేను. ఈ లోడ్ అను ఈ సెక్షన్ కి లోడ్ ఎలా ఉంది? పర్పెండిక్యులర్ 90 డిగ్రీస్ లో ఉందా, ప్యారలల్ ఉందా? అంటే ఏంటి పర్పెండిక్యులర్ అంటే నార్మల్ అని చెప్పాం కదా, 90 డిగ్రీస్ ఉంటే నార్మల్ అని చెప్పాం కదా, ఇక్కడ నార్మల్ లోడ్ అయింది. సో అదే ఇక్కడికి వస్తే ఏమైంది నీకు ఇన్స్టెంట్? ఇక్కడికి వచ్చిన కేసులో ఏమైంది? ఇక్కడ సెక్షన్ ఉంది, నాకు సెక్షన్ ఇది, నా లోడ్ నేను ఇలా ఉందన్న, లోడ్ ఎలా ఉంది ఇప్పుడు సెక్షన్ కి? పర్పెండిక్యులర్ ఉందా, టాంజెన్షియల్ ఉందా క్రాస్ సెక్షన్ కి? So therefore what kind of stress will induce in the bar, in the pin now? Because the load is a shear load, shear stress will induce in the pin. రైట్, క్లియర్ అయిందా? ఇప్పుడు ఎందుకంటే ఇదే బేసిక్స్, మనకి ఈ బేసిక్స్ వస్తే నెక్స్ట్ అన్ని ప్రాబ్లమ్స్ ఇవే ఉండేది మనకి. నార్మల్ స్ట్రెస్ క్యాలిక్యులేట్ చేయడం, షియర్ స్ట్రెస్ క్యాలిక్యులేట్ చేయడం, లేదా టార్షన్ మూమెంట్, టార్షన్ వల్ల టార్షన్ షియర్ ఏంటి, అట్లా కాకుండా నీకు ట్రాన్స్ఫర్ షియర్ అని ఇంకోటి కూడా ఉంది. బీమ్లోకి వస్తే నీకు ట్రాన్స్ఫర్ షియర్ ఫోర్స్ కూడా ఉంటుంది. ట్రాన్స్ఫర్ షియర్ ఫోర్స్ వల్ల నీకు మళ్ళీ దాంట్లో షియర్ స్ట్రెస్ ఉంటుంది, అది ఇంకోటి, అది కూడా విల్ సీ దట్ లేటర్. సో దీస్ ఫండమెంటల్స్ ఆర్ వెరీ ఇంపార్టెంట్. వన్స్ యూ అండర్స్టాండ్ దిస్, దెన్ ఇట్ ఈస్ ఈజీ. సో ఇట్ ఈస్ నాట్ ఏ న్యూ థింగ్. నువ్వు ఫస్ట్ ఇయర్లో, సెకండ్ ఇయర్లో అంత చదివి ఉంటావు దీని గురించి. సో ఇక్కడికి వచ్చి కొత్తగా నేనేం చెప్పట్లేదు, జస్ట్ ఉన్నదాన్ని రీకాల్ చేస్తున్నా, ఆ ఫండమెంటల్స్నే రీకాల్ చేస్తున్నా. ఇది అర్థం కాకపోతే సో నెక్స్ట్ ముందుకు వెళ్ళడానికి కొంచెం డిఫికల్ట్ అవుతుంది. సో ఇప్పుడు ఇది షియర్ లోడ్ అని అందరికి అర్థమైందా? ఇంకేమైనా అడిషనల్ ఎక్స్ప్లెనేషన్ కావాలా? దట్స్ వాట్ ఐ వాంట్ టు నో. సో ఎవరు రెస్పాండ్ అవ్వలేదంటే అందరు క్లియర్ అన్నట్టే. ఐ థింక్ దట్ ఎవ్రీబడి will understand it. So therefore what happens here is it is subjected to a shear load. So because of the shear load, so here the pin is shearing here as well as here, two locations. Oka location lo shear avutla, so it is shearing at two locations. So therefore I'll call it as a double shear. So suppose if the pin is there only up to this point, ikkada varake undi pin. So ikkada daaka ledu, only pin length taggichesi ikkada varake పెట్టారు. Then in that case it is shearing only one location. So I can say it is a single shear. But pin is from this point to this point, from this point to this point. It is shearing at two locations, so that I call it as a double shear. So therefore, the total shearing area, while calculating the total shearing area, what you need to do is, you need to calculate 2A, because the pin is in double shear. So you have to take 2A. So area, if I take dP is the diameter of the pin, so then the area at this location is nothing but pi by 4 into dP square. So I need to multiply that one by 2, then I'll get the shear area. So once I have a shear area, I have shear load 80 kilonewtons, and I have a shear area. So then shear load divided by shear area is nothing but shear stress. So we'll get from that you'll get allowable individual shear stress. Then you take the permissible shear stress value and equate it to that. You will get from that you will get what is the diameter of this pin also. Okay, so that I will show it in the next 2 slides. So the calculation part I will show it. This is the explanation how we can solve the problem. Then I show the calculation in the next slide. So the first, this is the given data. He has given P is 80 kilonewtons. That 80 kilonewtons is converted into newtons just by multiplying 10 cube, 80 into 10 cube newtons. Then this is the allowable stress value in tension. He has given 100 Newton per mm square. And this is the allowable shear stress in the pin, which is 80 Newton per mm square. So first we are considering the diameter of the bars. So which is same, like I already explained to you. So dV is the diameter of the bar, he has taken that. Then area of the bar is nothing but 5 by 4 into dB square. If you do that, you will get 0.7854 into dB square. Then the permissible tensile stress equations, this is the design equation. So your permissible tensile stress should be equal to P by AB. So P is 80 into 10 cube, and AB we got it as something like this. So now I equated 100 to this one, 101.846 divided by dB square. If I solve this equation, from that I'll get dB as 32 mm. So the diameter of the rod is, now it is 32 mm. So then we'll move on to diameter of the pin. So for that, again, we require this and this, load and this. So then he has taken the diameter of the pin as dP, and also he has taken the units are in mm. So that is also important. So then shear resisting area. So he has taken that as AP. So 2, why he has taken 2 is already I explained, because there are shearing taking place at 2 locations. So we call it as double shear. So therefore you need to multiply that one by 2. 5 by 4 into dP square, which comes out as 1.571 into dP square. Then we'll use the design equation. That is, the permissible stresses should be equal to the individual stress. So permissible stress is 80 MPa or 80 Newton per mm square, and individual stress we are calculating it is 80. The load is 80 into 10 cube, and the area is this. So if we equate those two, from that you will get an equation. If you solve that equation, you will get the diameter of the pin as 25.2 mm. So like this you can solve the problem. So when there is direct shear stress, you can design it. When direct, this is only direct shear stress, and you have a direct tensile stress. So maybe we'll see some more examples. Next problem is, I think it is on torsional shear stress, and similarly we will consider some more problems on bending moment also, and also some problems on eccentric loading also. We'll discuss all those things in the coming classes. Today I'm stopping at this point. So we'll continue in the next class. So before closing it, if you have any doubt now, then you can ask it. Or those who have understand everything, they can leave. So those who have doubt, you can ask them doubt. I think somebody is writing a shear load. Okay. Some comments regarding those questions. Okay, I think most of you will be leaving. So I think if there is no doubt, then I'll close it.
Sir.
Yes. Yeah, tell me.
Sir, అంటే షియర్ స్ట్రెస్ అంటే షియర్ లోడ్ జరిగినప్పుడు ప్రతిసారి అప్పుడు 2A వచ్చింది కదా సార్, ఇంటూ ఏరియా చేసుకున్నప్పుడు.
షియర్
ప్రతి ప్రాబ్లం ఇది
ప్రతి ప్రాబ్లం
అంటే షియర్
You won't get
అంటే shear లో-
you will get double shear. So double shear, single shear. నీకు అంత ముందు ఒక ఎగ్జాంపుల్ నేను చూపించా సింగిల్ షియర్ కి. ఏది ల్యాబ్ జాయింట్ తీసుకున్నాం మనం రివిటెడ్ జాయింట్స్ లో ల్యాబ్ జాయింట్ చూపించాను నీకు. ల్యాబ్ జాయింట్
Yes, sir.
అక్కడ మనం డబల్ షియర్ తీసుకోలేదు కదా, సింగిల్ షియర్ ఎందుకు తీసుకున్నాం అక్కడ?
ఓకే సార్, అంటే 2 ప్లేట్స్ మధ్యలో కంపేర్
స్లైడ్ చూపిస్తా ఉంటా ఒకసారి నీకు. ఇక్కడ ఉంది కదా ల్యాబ్ జాయింట్ ఉంది. ఎక్కడ షియర్ అవుతుంది? ఓన్లీ ఈ లొకేషన్ లోనే షియర్ అవుతుంది. ఈ లోడ్ ఇక్కడ ట్రాన్స్ఫర్ చేశాను నేను, ఈ లోడ్ ఇక్కడ ట్రాన్స్ఫర్ చేశాను. ఓన్లీ ద షియరింగ్ ఈస్ టేకింగ్ ప్లేస్ ఓన్లీ అట్ దిస్ లొకేషన్. ఒక్క లొకేషన్ లోనే కదా. ఇక్కడేం రాస్తావు? దీని కేసులో ద షియరింగ్ ఏరియా ఇస్ గోయింగ్ టు బి ఓన్లీ 5/4 d² ఓన్లీ. ఒక్క లొకేషన్ లోనే షియర్ అవుతుంది అది.
ఓకే సార్.
సో ఈ పర్టికులర్ కేసుకు ఈ ప్రాబ్లంకి వచ్చేసరికి ఏంటంటే ఇక్కడ షీర్ అవుతుంది, ఇక్కడ షీర్ అవుతుంది. ఎందుకంటే నువ్వు ఈ రాడ్ని ఇలా పుల్ చేస్తున్నావు, ఈ రాడ్ని ఇలా పుల్ చేస్తున్నావు. అంటే ఇక్కడ రిలేటివ్ స్లైడింగ్ ఉందా? ఈ రాడ్ ఏమో ఈ లొకేషన్ లో ఇటువైపు మూవ్ అవుతుంది, ఇదేమో ఈ ఫోర్క్ ఇటువైపు మూవ్ అవుతుంది. అంటే రిలేటివ్ స్లైడింగ్ ఉందా ఇక్కడ? అందుకని ఇక్కడ షీర్ అవుతుంది. అట్లానే ఇక్కడ కూడా ఏమైంది? ఈ పోర్షన్ ఆఫ్ ద రాడ్ ఇటు మూవ్ అవుతుంది, ఈ పోర్షన్ ఆఫ్ ద ఫోర్క్ ఇటు మూవ్ అవుతుంది. కాబట్టి ఇక్కడ కూడా స్లైడింగ్ ఉంటుంది, రిలేటివ్ స్లైడింగ్. అంటే ఏంటి? ఇక్కడ షీర్ అవుతుంది, ఇక్కడ షియర్ అవుతుంది. సో దెన్ విల్ కాల్ ఇట్ యాజ్ డబుల్ షియర్. అదే ప్రీవియస్ రివిట్ ఎగ్జాంపుల్ తీసుకుంటే ఏమైంది? ఓన్లీ ఇక్కడే షియర్ అవుతుంది, అది ఎక్కడ అవ్వట్లేదు కదా. సో నీకు డౌట్ రావచ్చు, ఇక్కడ ఈ రివిటెడ్ ఉంది కదా, ఇక్కడ కూడా షియర్ అవ్వచ్చు, ఇక్కడ కూడా అవ్వచ్చు. సో అవ్వచ్చు, కానీ అది రివిటెడ్ కింద వెళ్తుంది కాబట్టి ఈ డయామీటర్ కింద రాదుగా. దట్ ఈస్ అ డిఫరెంట్ థింగ్.
ఓకే సార్.
ఓకే, క్లియర్?
సార్. థాంక్యూ సార్.
ఓకే, నెక్స్ట్ ఎనీ అదర్ డౌట్?